So I just got news today that it got delayed again. So this amazing telescope was supposed to be launched on the 24th. Is scheduled now for the 25th, early in the morning, as soon as possible. And the reason for the delay this time was weather, simply. The weather forecast wasn't good for the 24th. One interesting thing, if you have a telescope in your house, is that you can try to see the telescope up in space on the 25th at night. If you look at Orion, a little bit south of Orion's belt, you should see a small dot, and that will be the telescope. It will be moving slowly towards the Horse Nebula, I think. So that's just a fun fact. The James Webb is an amazing telescope. It's going to be the successor of the Hubble telescope, by far the most successful telescope we had in the last 2 decades. And one very delicate part of this telescope is going to be its journey to its final destination, which is going to be the Lagrange Point 2. This point is about 10 times the distance from here to the moon, and it's in the opposite direction between the axes formed by the sun and the Earth. It's the point where the centrifugal force and the gravitational force due to the sun, the Earth, and the moon will cancel. So it's a very stable point. It's good for deep observations, especially in the infrared, which is what this telescope is. It's a telescope in infrared. It cannot be around the Earth because the Earth is relatively hot, and it would contaminate some of the signal. Once it's in L2, it will be on the bottom left. You can see a little cartoon of how it will be in relation to the sun. It will have its solar shields between the telescope and the sun, protecting the detectors from the sun, just to keep it as cool as possible, again, because this is going to be observing in infrared. And it will be able to pitch or rotate an angle of 50 degrees, always trying to stay on the shade of the sun shields. This journey to the L2 point, it's going to be very tricky, as I was saying. On the top right, you see Roger Windhorst. He's one of the PIs for one of the proposals we have already approved to observe some interesting objects with the James Webb. And that's an old picture, but I imagine this is what he's going to look like in the next month. He's going to be praying that everything goes right, because there is a lot of things that can go wrong. In particular, NASA identified about 350 critical points, things that can go wrong, and any single one of those will be a disaster for the telescope. About 80% of those, 270 or something like that, have to do with the deployment of the telescope. The telescope has to unfold the solar panels, the sun shield, the telescope itself is folded, it's not traveling in one piece. And if any of those 270 points fails during the deployment, the whole mission may be a risk. Little story, one of the tests that was done a few months ago before it was put together and shipped to the French Guiana, it was a vibration test where the telescope is shaken, trying to mimic the launch in the Ariane rocket. And during that test, something like 20 volts, something like that, fell off the telescope. That resulted in one of the multiple delays this telescope has had. It was supposed to be launched like 14 years ago, but this falling of these bolts made the engineers, they had to redesign all the bolts, because they were designed in such a way that they only turn once in order to save weight. So they had to redesign all the bolts, so now they turn twice, which is incredible. Just they added a few more grams of weight to the telescope, but that represented a few months delay for the entire mission. And even more, once the telescope is in L2, the other amazing thing about this telescope is that everything has to fall in place. And this is not just a simple sentence. The telescope has been designed on Earth with known errors and mistakes. The optics are not perfect here on Earth, but they are expected to be perfect once it cools down at minus 170. I don't know what's the temperature, I don't remember. It's very cold. Due to this very cold temperature, all the metal components, everything will change shape a little bit. So everything is supposed to fall in place at that temperature. But when it was designed and built here on Earth, everything was built knowingly with their own shape and parameters. Which is something still blows my mind. As I said earlier, this is the successor of the Hubble telescope. This is a quick comparison. The mirror itself, which is the main component of the telescope, it's in area is about a factor 10 times larger, so it can collect 10 times more light in the same amount of time. The other interesting difference is the frequency range. Hubble was mostly working in the optical, a little bit of the UV and a little bit of the infrared, but it was mostly an optical telescope. James Webb is clearly going to be an infrared telescope, near infrared and mid infrared. And the other big difference between the two telescopes is that the James Webb is going to have a lot more spectroscopic capabilities. It's going to have multiple modes to do spectrum of different objects, and that's going to open new doors to do interesting science. This is going to be a golden age for astronomy, and the golden is not a free word here. The mirror itself is coated in gold. As far as I know, it's the first telescope that is using gold in its mirror. And the reason for that, again, is because it will be working on the infrared. And here on the bottom panel, you see the reflectance of different metals normally used in mirrors. Aluminum is a common one, silver in some telescopes, but gold, you can see that in the infrared is the winning metal, right? On the picture on the left, you see another PI from another proposal we have. This is Dan Coe. This is an actual picture he took when the telescope, or a model of the telescope, was on exhibit. The instruments in the James Webb are mostly 4 instruments. NIRCam in the center. This is the focal plane of the instrument. It's not a regular shape. It has instruments in different areas. NIRCam is towards the middle and is the main instrument for doing imaging. Then NIRSPEC on the left, it will be mostly the main instrument to do spectroscopy. And one interesting thing about this instrument is it has these micro shutters. There's a picture in the bottom where you can basically put a slit anywhere you want in the image, and you can design the shape of the slit. You can make it straight, you can make it smaller, larger. It's going to add a lot of flexibility. Then there is NIRIS, which is going to do mostly spectroscopy, but with prisms. So that's a different type of spectroscopy. And then MIRI, which part of the camera was developed here in Spain, in Madrid in particular. It's going to be the main instrument for the mid-infrared, going up to 20 or 30 microns, which is going to be incredible for some type of science, especially planets and things like that. There is also something that didn't have the Hubble, which are coronagraphs, which will be used to do high contrast imaging, but also to observe exoplanets directly by blocking the light, or most of the light, from the central star. And there's in particular, I think there's like 5 proposals already to point the telescope to TRAPPIST-1 star, which is known to have, I don't remember if it was up to 5 or 7 exoplanets, rocky planets with masses similar to Earth, and at least there is 1 or 2 that we know that are supposed to be in the habitable zone, meaning they could have water and life and everything. Really quick, this is the different capabilities of the James Webb to do spectrum. And this is one of the techniques that will be used to study exoplanets, and in particular their atmospheres and the possibility that they could have life. For instance, by looking at oxygen. Oxygen is very difficult to have oxygen in an atmosphere unless you have something that is continuously pumping oxygen, in particular life forms. Just to give an idea of the type of science that the James Webb can do, this is just a compilation of the first program with all the proposals that were approved, grouped by topic. And this is the first open program. There are other programs. One is the early release, and the other one is the guaranteed time. But this is just the first program where anybody can apply. And you can see that most of the proposals are going to be dedicated to do galaxies and exoplanets. But then there are many proposals that will be studying stellar environments and even astronomy in the solar system. This is about 6,000 hours per year. A year has about 8,000 or so. So the rest of the time it will be used for calibration, servicing the telescope and things like that. But about 6,000 hours every year will be used for science. Why infrared? Well, infrared is difficult to do from the ground here, from Earth. Atmosphere. It has a lot of absorption features. So the best place to do infrared is in space. But infrared is useful not only because it tells you, well, it is useful because you can see things that you cannot see in the visible light. In particular, parts of the universe become more transparent. Like this is an image. This is actually taken with the Hubble telescope. In the left is what you would see in the optical, and in the right is what you can see with the infrared, and you can see through some of these dust clouds. But also, infrared is useful because you can see farther away. The next slide will show this better, but this is one example of what we expect to see with the James Webb. Again, this is an image taken with the Hubble telescope, but this is the deepest image that has been ever done with any telescope, in particular with the Hubble. Well, I don't know if it's the deepest. There is another image taken with some of the large ground telescopes, but they are equally deep as this. But to take this image, it took about 500 hours of exposure. It's like taking a picture for 500 hours and keeping the camera still. That's incredible. And this is a tiny area of the sky, and you can see up to more than actually 5,000 galaxies in this small area. So Hubble can take this kind of images in a fraction of its time, in something like 30, 40 hours, can do something similar to this. And not only reach this depth, but see galaxies that you wouldn't see even with the Hubble because of the spectral signature of these galaxies. If you look first at the panel here in the bottom, you see that between 2 and 20 microns, most galaxies have a peak in the emission. And if these galaxies are at redshift 7, you would see these galaxies brighter. They're at redshift 7, you would see them brighter only if you can take a picture of them with a camera that is sensitive to 2 to 20 microns. Hubble cannot do that. Hubble goes up to 1.6, it doesn't reach 2. So this is one of the reasons why the James Webb is built, to see these galaxies beyond redshift 7. If you want to go even further, at redshift 10 or so, there is another peak in the emission at lower wavelengths, and that's the Lyman alpha and all the associated emission. And you would see that in the infrared if the galaxies are redshift 10. So if the galaxies are redshift 10 and you are not sensitive to these wavelengths, you don't see these galaxies. So again, James Webb will be hunting for these galaxies, and these galaxies are critical to understand how the universe re-ionize, which is a critical period in the age of the universe that we don't fully understand yet. But these first galaxies, the ones that form first, are the ones that, in theory, re-ionize the universe. And with the James Webb, we'll be able to understand that process. and understand how galaxies are born and they grow in those early days. As part of one of the programs I was mentioning, this is one of them. It's over 100 hours that we have granted with the James Webb. The PI is Roger, is this guy I saw you earlier that was kind of praying, or is going to be praying for this first month. We're going to be observing a bunch of clusters and some areas in the sky, like the North Ecliptic Pole. We'll be studying many things, like distant galaxies and things like that, but we'll also be studying dark matter in galaxy clusters, in particular this one. This is a Gordo cluster, and the analysis for this cluster will be led from here, from IFCA. So we'll be busy with this one once it is observed. So not only dark matter and distant galaxies, we also have time to observe stars, a high redshift. In particular, this one. This is not published yet, but there is a star at redshift 6 that was observed with the Hubble and with the James Webb, and we got over 10 hours to see this star. It's not the one I have in this image. This is another one, but it's similar. It's a similar effect. So this will be also a very interesting work that will be done with the James Webb, where we will be participating here from IFCA. The other big subject where the James Webb will be a game changer will be studying exoplanets. As I mentioned earlier, there's already some proposals in place, and there's a lot of excitement because James Webb can study these exoplanets in ways we haven't been able to study them before. In particular, in the infrared, you can see the atmospheres of these planets. When one of these planets passes in front of the star, where they are orbiting around, you can see with the James Webb absorption features in their atmospheres, for instance. Also with the coronagraphs that the different instruments have, you can block the light of the star for most of the light and actually have a chance to see directly the planet, not just the shade that the planet produces when it goes in front of the star, which is the typical method to detect these planets, but you can actually see the planet and how it moves as it orbits the star. So that's going to be super exciting. And the same thing that happened with the Hubble, possibly the most exciting results with the James Webb are the ones that we haven't even planned for. People are putting proposals to observe very concrete and particular things, but with the Hubble, it did happen that the most interesting results and the ones that were able to advance the field more than any other thing were the ones that nobody thought about before. And this is something that we hope it will happen again with the James Webb. It's going to open a new window into unknown territory. So we have some ideas of what to expect, but there's definitely going to be surprises. I just put this one. This was a cool discovery made years ago, not by Hubble, but it was studied with Hubble a little bit. And it's this hypothesized, I don't know the word, hypothetical Dyson Spheres, which are a sign of life that appear in some science fiction books. There's been a couple objects already which match this kind of description. It's possibly something else. I'm not saying we have found aliens, but it is true that the James Webb, for instance, with this capability to detect the components of atmospheres, can study if there is some civilization there. Why not? The same way somebody is studying Earth from a distant star could tell that we are polluting the planet and trusting it. So anyway, the unexpected is probably what is going to be the most exciting stuff with the James Webb. Hopefully everything goes well. We have a month ahead of us where hundreds of things can go wrong, and there is only one way to get it right. So let's hope for that. This is my last slide. Thank you.